We design products using 3D CAD tools, but the finite element method does not use these solid model geometries directly in its calculations. Instead, we need to divide the solid model into simpler elements in a process called meshing, and the solver constructs a system of equations based on the nodes and elements of this mesh. In mechanical APDL, we can create solid model geometry and generate a mesh using APDL scripting. In this video, we will discuss different strategies of generating a mesh, the rules for modeling solids and manipulating them, the workflow for meshing, and a demonstration of creating a simple ball grid array, then meshing it using an APDL script in interactive mode. Okay, let's get started. An element is the building block of a finite element model, and the proper definition of its characteristics is crucial for the analysis. In mechanical APDL, there are some element attributes that need to be defined before generating a mesh. We start with the element type, which is the most important attribute since it determines the physics, dimensionality, degrees of freedom, and several other important element options. A pictorial summary of element types and their physics can be found in the Mechanical APDL Help Element Reference Guide, Chapter 2 on Element Classifications, Summary of Element Types. Another important attribute is the element coordinate system, which determines the orientation of material properties and element results such as stresses. By default, the element coordinate system for a solid element is aligned with the global Cartesian coordinate system, and we need not define it unless a different orientation is preferred. Material properties are another important element attribute that are used, for example, in calculating the stiffness of an element in structural simulations. Sometimes we may need to supply additional information in the form of real constants or section properties, such as the thickness of shell elements, as part of the element attributes. While the element coordinate systems and other element attributes can be defined after the mesh is generated, the element type must be defined prior to meshing. Once the mesh is generated, each element and node is assigned a unique identification number, which may be used to refer to them. Typically, once the element attributes are defined, we can obtain a mesh in one of three ways. The first is direct generation. In this method, the nodes and elements are generated by the user manually using an APDL command such as N for defining a single node and E or EN to define a single element. Nodes and elements are directly defined by the user, which makes it cumbersome and impractical for most situations involving complex geometry. However, for simple abstractions, such as a point mass or a one-dimensional spring or damper element, direct generation is quick and easy. The second method is to generate a mesh from CAD geometry. In this method, a solid model that is either created within mechanical APDL or imported from an external CAD software is used as a starting point and meshed with mechanical APDL. The node and element numbering are done automatically. Lastly, we can also import and work with meshes that are generated by other preprocessors, such as Workbench Mechanical. The node and element numbers are imported with the rest of the mesh details. In this video, we'll focus on creating solid models and meshing them with mechanical APDL using APDL scripting. But before we get into it, let's look at importing external CAD geometry of IDIS files into mechanical APDL. One can do this using the import functionality in the mechanical APDL GUI or using the APDL command idisn. One can import an IDIS file using the command idisn, file name, extension. There are other CAD file formats that mechanical APDL supports, but they usually require configuring the appropriate geometry interface, which may require an additional license. Details of the supported file formats and their software and license requirements are available in the Connection User's Guide of the Mechanical APDL Help. Now, let's talk about solid modeling. In mechanical APDL, solids follow a hierarchy, with key points being at the bottom and volumes at the top. Key points are vertices. Lines are the edges created from two or more key points. Areas are the faces that are created by lines enclosing them. And volumes are created from a set of watertight areas enclosing a three-dimensional space. Except for primitives that are discussed shortly, in building a model, one cannot create the higher order entity without creating the lower order entities first. For instance, we cannot create a line without first defining the key points of the line. Each geometric entity has a unique ID number, which is often generated automatically. So, care must be taken while writing scripts to use the correct ID number. If you need to work with multiple geometric entities at the same time, you can group them by creating components using the cm command, which with an assigned user-defined name. Selecting by a component name is often easier than trying to select all the component members by ID number. Also, some APDL commands allow referencing by component names. Due to the hierarchy, a low-order entity cannot be deleted if it's attached to a high-order entity. When modeling solids in mechanical APL, there are two approaches that can be used together. A bottom-up approach, where the lower-order entities are created first, then the higher-order entities are defined, and a top-down approach, where area and volume primitives, such as rectangles, circles, cylinders, cones, etc., are created directly. Note that in a top-down approach, even though a high-order entity is first created, the lower-order entities that form it are generated automatically. While modeling solids, one can freely interchange between a top-down and a bottom-up approach. There are several solid operations that are available in mechanical APDL. Drag and rotate are some common operations used for constructing solids. For instance, we can create a line by dragging key points. You can drag a line to create an area, and drag an area to create a volume. Similarly, we can also rotate the lower order entities to create higher order entities. We can also modify existing entities using moving, copying, and scaling operations. In the case of copying, we can create multiple entities based on an existing entity, which is very useful with their repetitive features in the geometry. Each of these operations have corresponding lists of commands that can be operate on key points, lines, areas, or volumes. In addition to these, we can sculpt a model using Boolean operations such as union or addition, intersection, and subtraction. These operations can be done on solids created by both top-down and bottom-up approaches. For instance, if we wish to create a hole in a part that is created by a bottom-up approach, we can create a cylinder as a primitive in the location of the hole and use the subtract Boolean to cut out the hole from the part. Often, Boolean operations are used in tandem with copying and moving operations in creating complex geometries and assemblies. While this is not the entirety, the discussion so far provides a good overview of solid modeling in mechanical APDL. So let's move on to the next topic of this video, which is meshing. The goal of developing a finite element model is to represent the system as a mesh of nodes and elements. The typical workflow for generating a mesh in mechanical APDL is to first define the element attributes, then define the mesh controls, and then to generate the mesh. It's important to note that in mechanical APDL, while generating a mesh from solid bodies, the mesh is tightly bound to the underlying geometry, so we cannot delete the bodies without clearing the mesh first. Also, the dimensionality of the solid should match the dimensionality of the element type. For instance, we cannot define an element type with solid 185, which is a 3D element, and use it to mesh areas. Depending on the application and geometry, one may choose between generating a free or a map mesh. A free mesh has no restrictions in 2D on element shapes, and there is no pattern to the way the mesh is generated. In 3D, the mesh is usually restricted to tetrahedral elements. This unstructured strategy is helpful in meshing complex geometry. On the other hand, a map mesh results in either an all quad or all tri elements in 2D and all hex elements in 3D, and there is a pattern with obvious rows and elements. This structured strategy works with geometries made of regular areas or volumes. One can choose between either of these strategies using the mesh key command. In conjunction, one can also use the command mshape to pick all tet tri or all hex quad elements. For instance, if we issue the commands mesh key, 0 and mshape, 1, 3D, then the meshing algorithm generates a free mesh with all tetrahedral elements. There are a few mesh controls that are typically used while meshing, such as esize, which is used to define a default element size of lines, and xesize for defining local element sizes, where x stands for L's for lines, A for areas, and V for volumes. To generate a mesh, one can use xmesh command on geometric entities individually or in groups, where again the X can stand for L for lines, etc. The resulting mesh on one entity could be used to control the mesh size on others that share the geometric connections. For example, two areas that share a line. Another useful mesh generation command is vsweep, which is used to fill a volume with elements by sweeping a mesh boundary area of the volume through the volume. That concludes our discussion on meshing, but before we proceed to the demo, let's look at the Modeling and Meshing manual in the help documentation. Both solid modeling and meshing have several options in mechanical APDL, which can be used to model and mesh most geometries. It's not practical to keep a track of all the commands associated with them, and therefore this manual can come in very handy. It discusses different commands and several strategies available for both modeling and meshing in mechanical APDL. With this knowledge, now let's proceed to the demo where we develop the geometry and mesh a ball grid array using an APDL script. A ball grid array is a type of surface mount packaging used in the semiconductor industry. It has a grid of solder balls that form a permanent connection between the die and the package. It establishes an electrical connection between the two parts and is therefore subject to thermal stresses and thermal fatigue. Due to these reasons, structural and thermal analysis of ball grid arrays is of great interest in the semiconductor industry. In this demo, we'll write an APDL script to define the dimensions as parameters, develop the geometry, and then mesh it. This way we can automate design iterations with ease. The ball grid array is a 3x3 grid of spheres of radius r that are sandwiched between two plates of length, width, thickness, x, z, and y. We wish to generate a mesh that is suitable for thermal analysis, so we'll use solid 70 elements. We start the program with finish and /clear commands. Next, we define all independent and dependent parameters. In this demo, we'll use the equality operator to define the variables. Note that the dimensions x and z are dependent on the number of solder balls, as the plate dimensions must accommodate the array. Therefore, we define them as dependent parameters. Note that all the following steps fall under the pre-processing stage, so we enter the processor /prep7 by issuing the session command. As a first step, define all the necessary element types and attributes. In this example, we intend to use the mesh for thermal analysis, so we pick the element type solid 70. So, define the element attributes using the ET command. Next, we create two plates using these dimensions. In this example, we'll use the command block, which is used to create a block between 2 points. Now, let's create a few components for the entities created so far. Components are a group of common entities such as line, areas, volumes, nodes, or elements that can be grouped and identified easily. These are created using the cm command. Start by creating a component called block for both of the plates. Next, select the two inner planes of the blocks using the ASEL command and create a component for each of the areas and name them area_1 and area_2. Once the components are created, change the active selection to all parts using the allSelect command. Next, create a sphere of radius r for the cornermost solder bump. In this example, we'll use the command sph4 to create a sphere of radius r at the corner. Now, slice the sphere using the two areas selected earlier. To do this, first unselect the component block from active selection so that it isn't affected by slicing. Now, slice the active volumes, which is the sphere, by the two components area 1 and area 2 using the VSBA command. This creates the solder between the two plates and two overlapping volumes, which are not needed. So, we'll delete these two partial spheres. To do this, unselect the volumes whose location is in between the planes using the VSEL command. This leaves us with just the overlapping volumes, so go ahead and delete them using the VDELE command. Change the active selection back to all the components using the allSelect command. Now that we're left with just the two plates and the solder ball without overlapping, let's generate a pattern of a 3x3 grid on the remaining solder ball. To do this, first unselect the block component from the active selection, and then issue the vgen command once to create a first row of solder balls, and then issue another vgen command to fill the columns. This creates a grid of solder balls since all the solder balls are under active selection. Create a volume component named solder to group all solder balls together. Now that all the volumes are generated, select all components using the allSelect command, then use the vglue command to combine all volumes into one so a conformal mesh is generated at the interface when we mesh. Note that the vglue performs a Boolean operation on these parts. This completes the modeling part, so let's proceed with meshing. Due to a combination of spherical and block geometries, a map mesh can be tricky to generate, so let's use a free mesh. Issue mesh key, 0 command to make this choice. Also, let's use all tetrahedral elements due to the complex geometry. Issue mshape, 1, 3D command to make this selection. Next, let's issue mesh size controls using the command smrt. It uses a scale of 1 to 10 to define the mesh density, with 1 being coarse and 10 being fine. Let's use 6 for this demo. Before we generate the mesh, let's assign material IDs to all the volumes. Since the plates and solder balls have different material properties, we need to assign a different material card for each. Select the component block and issue mat,1 to assign material ID 1 to the plates. The blocks are ready to be meshed, so go ahead and mesh it by issuing vmesh, all. Next, select the component solder and issue mat,2 to assign material ID 2 to the solder balls. Go ahead and mesh the solder balls using the vmesh command. Finally, plot the elements to visually inspect the mesh. This can be done with the eplot command, but before issuing it, let's define some view controls for a better visual purpose. We'll select all the volumes except for the top plate so we can visualize the mesh of the solder balls when we plot. Next, let's use some material ID numbering on the elements so the materials with different IDs appear in different colors. Finally, set the view orientation to isometric view using the /view command. Now issue the eplot so the elements are plotted. This finishes the workflow, so save the database using the save command. That concludes the workflow. We have developed an APDL script that can generate a 3x3 grid array and mesh it in an APDL. This concludes the video on solid modeling and meshing using APDL scripting.